So, good afternoon, everybody. Myself, Acharya Vishvendra. Let's discuss NCERT line to line today. And we are discussing chapter 14, which is semiconductors. So, let's start with the question number direction of hole current and electron current. So, these add up. So, these are in the same direction. The first is correct over here. Next is total current is sum of current due to electron and due to the holes. Next is at equilibrium in an intrinsic semiconductor for electron hole pairs, rate of combination. So at equilibrium both rates are same. So second is correct over here. Next is moment of hole in a crystal of silicon is same direction as that of it's in opposite direction as that of bonding electrons movement. So second is correct over here. Next is electron gets excited at higher temperature from valence band to conduction band due to thermal energy. Next is energy band diagram of semiconductor at 0. So at 0 Kelvin it behaves as pure insulator. So all the electrons are in the valence band. So first corresponds to the correct configuration. Next is in the above question, energy band diagrams at T greater than 0. So obviously some electrons will move to the conduction band. So that will be corrected by 2. 2 will be the correct option over here. Next is order of ionization energy of carbon, silicon and germanium is. So obviously carbon is non-metal, it has got highest energy, then silicon, then germanium. So first one will be correct. Next is conductivity of an intrinsic semiconductor. Depends on temperature, independent of temperature. Yes, so conductivity of an intrinsic semiconductor. So conductivity, it depends on temperature. First one will be correct over here. Next is at room temperature, conductivity of intrinsic semiconductor. This is very low. Second is correct. Next is conductivity of intrinsic semiconductor can be improved by one of the ways to increase the temperature. Another is to use certain impurities. So both are correct. So third will be correct here. Next is extrinsic semiconductors are also called. These are called impure semiconductors because we have to dope them with either group 15 or group 13 elements. Next is deliberate addition of a desirable impurity is called. This is called doping. Next is impurity atoms are called. So the impurity atoms are called the dopants obviously. Next is extrinsic semiconductors are also called. These are also called doped semiconductors because these are obtained by doping. Next is the dopants have to be such that the original configuration is not disturbed. So the sizes have to be approximately the same. Next is in doping, the dopant occupy a large number of originals. No, it's only a few original semiconductor sites. It's generally in the order of ppm, particle per million. That is only one site out of 1 million, that is 10 is to power 6 elements are they are occupied by the doped impurities. Next is size of dopant and semiconductor should be they should be nearly the same so that they can adjust well into the crystal. Next is how many types of dopants are used in doping tetravalent, silicon or germanium. There are generally two types. One is either from the 13th group or from the 15th group. Next is pentavalent dopants are. So pentavalents are group 15th element which includes phosphorus, arsenic, antimony. So these all are the pentavalent dopants. Next is trivalent, they belongs to the 13th group which is boron, aluminum, indium. So all option will be correct over here. Next is silicon and germanium belongs to. So these belongs to the obviously fourth group of the periodic table. So second is correct over here. Next is dopant elements are chosen from third or fifth group so that because of the size is nearly the same, so they are chosen from the third or the fifth group. So first is correct over here. Next is N-type semiconductors are formed. N-type semiconductors are formed when silicon or germanium are doped with obviously pentavalent impurities. Next is in N-type semiconductors, when dopant's atom share its electron cloud with the original atom, the ionization energy is minimum for 4 bonding electrons or the 5th electron. Obviously for the 5th electron because it is less tightly bound. So second is correct over here. Next is the energy required to move 5th electron in an extrinsic semiconductor of germanium is about. So for germanium it's about 0.01 electron volt. Next is in the above question energy for silicon is about, this is 0.05 electron volt for silicon. Next is for intrinsic semiconductors at room temperature. Forbidden band for germanium is about, this is about 0.72 electron volt for germanium. Next is forbidden band of silicon is about 1.1 electron volt. Second is correct over here. Next is in N-type semiconductors, impurity is called donor impurity. Obviously it donates one of the electron, so it is called the donor impurity. Next is number of electrons made available by donor impurity depends on doping level, ambient temperature or both. So it just depends on the doping level and is not dependent on the ambient temperature. Next is number of electrons made available by silicon atom in a doped semiconductor. So it increases weakly with temperature. As more the temperature, more will be the probability of breaking the bonds. So electron hole pair will be generated. So the number of electrons contributed by the silicon atom, the increases weakly with temperature. So second is correct over here. Next is N-type semiconductors are shown by, obviously this is the electron contributed by the fifth group elements, and as a result of this they get a positive charge. So first is correct over here. Next is in a doped semiconductor, total number of conduction electrons is due to, obviously some are generated by contributed by donors, whereas some are intrinsically generated. So both are correct. Third is correct over here. Next is in a N-type doped semiconductor, total number of holes is due to, obviously holes are intrinsically generated as the dopant or the impurity just gives electrons. So second is correct over here. Next is in N-type semiconductor, rate of recombination of holes will, obviously rate will increase as there are more electrons now, so there will be more probability of combining with holes. So first is correct over here. Next is in the above question, number of holes will, so certainly they will decrease. Next is in N-type semiconductors, electrons are majority charge carriers, so more electrons are there, so they are majority charge carriers. First is correct. Next is for N-type semiconductors, obviously electrons are majority charge carriers, so first is correct over here. Next is P-type are obtained, so obviously trivalent impurities. First is correct. Next is dopants have, they have one less valence electrons, so second is correct over here. Next is a P-type semiconductor, so obviously it is represented by second because it accepts electrons, so negative charge and the corresponding hole.